What is vapor pressure? I try to give you an idea. When liquid is kept in container, the molecules on the surface are more energetic than molecules underneath for obvious reasons. The surface molecules tend to escape to form vapor above the liquid surface. This phenomena is called evaporation. Evaporation continues until all the liquid evaporates. Now imagine the liquid in a closed container. What happened here? Liquid molecules on the surface evaporate, form vapor molecules. These vapor molecules again get trapped in the liquid phase. After some time, the two rates become equal. Then it seems that evaporation has stopped. This is a case of equilibrium where the rate of the two reactions become equal. At this point, the vapor molecules will exert some pressure to the container, and this pressure is called saturated vapor pressure at the existing temperature. Saturated vapor pressure varies with temperature. Now let's come to Raoult's law. It was observed that vapor pressure of liquids was reduced when some non-volatile solute is mixed with the liquid. It was thought that some liquid molecules on the surface has been replaced by molecules of the non-volatile solute. This depends on the number of moles of solute added. The more solute you add, the more number of liquid molecules get replaced at the surface. So the number of liquid molecules available for evaporation depends on the mole fraction of the liquid molecules. Raoult's law says that the vapor pressure will be equal to the mole fraction multiplied by the vapor pressure of the pure liquid. Now the question is, does the same reasoning hold good for liquid mixtures? Or in other words, can Raoult's law be applied to liquid mixtures? Strictly speaking, the answer is no. However, if the two liquids which are being mixed have almost equal intermolecular force, then the Raoult's law is almost valid. Now let me explain how liquid mixtures actually take place. Let the two components of liquid be A, which is red in color, and B, which is green in color. There must be some sort of intermolecular forces existing between A molecules and B molecules. If they are to mix, then these bonds, namely the AA and BB bonds, are to be broken. Suppose AA bond is very strong like water molecules which are bonded by hydrogen bond, and BB bond is very weak as in carbon tetrachloride where there is only weak van der Waals force. In that case, polar A molecule will have affinity towards another polar A molecule so much that it completely ignores non-polar B molecule. So there is no question of bond breaking and mixing does not take place at all, as we all know that water and carbon tetrachloride are immiscible. See how actual mixing takes place. It involves bond breaking of AA and BB bonds, and new AB bonds are made. Now bond breaking requires energy and bond making release energy. If the strength of these bonds are equal, then the energy of bond making and bond breaking will cancel each other, which imply that enthalpy of mixing is zero. The bond strength being equal, the bond lengths will also be the same, which imply that there will be no volume change while mixing. This type of mixture will obey Raoult's law and is called ideal mixture. This is represented in the vapor pressure composition diagram. This one is the vapor pressure of pure A liquid and this one is the vapor pressure of pure B liquid. Obeying Raoult's law, we may join the points by straight lines. The total vapor pressure is given by this line. Now, what is boiling point? It was said that vapor pressure is temperature dependent. Vapor pressure increases as temperature is increased. If we keep on increasing the vapor pressure by increasing the temperature, a stage will be reached when the vapor pressure will be equal to the external pressure, that is the atmospheric pressure, as in most cases. At this temperature, rapid evaporation takes place, not only from the liquid surface, but also from underneath, as we see the vapors emerge from the bottom in the form of bubble. This is called boiling point of liquid. If a liquid has more tendency to go to vapor phase, then it has high saturated vapor pressure and low boiling point. If a liquid has less tendency to vaporize, then it has low saturated vapor pressure and high boiling point. Like in the previous diagram, instead of vapor pressure, we measure boiling point at every possible composition. Since boiling point is not governed by Raoult's law, the boiling point curve will not be a straight line. It will be curved. At boiling point, the vapor phase will have a different composition than liquid mixture. The more volatile component will be richer in the vapor. We can condense the vapor and measure the composition and plot a curve of the vapor composition like this. We see that the composition of vapor and liquid is the same at a particular temperature only for pure liquids, that is, where the two curves meet at the end. For mixtures, say at composition X, if the liquid mixture is boiled, then its vapor composition will be Y at the same temperature. Composition Y clearly indicates that the vapor pressure will be more richer in the more volatile component. In actual practice, there is always deviation from Raoult's law. There are two types of deviations. Positive deviation. Here, AA bond strength and BB bond strength is more than AB bond strength. So the A or B molecules at the surface face not only the molecules of their own kind but also molecules of the other liquid. Since AB bond strength is less, so the pull of the surface molecules will be less than in pure liquid. Therefore, there is greater tendency to evaporate of both A and B than calculated by Raoult's law shown by these curves. Bond breaking energy is also more than bond making energy. So the enthalpy of mixing will be positive and the process of mixing will be endothermic. Also, the new AB bonds formed are weaker. Their bond lengths will be greater and the volume will increase after mixing. When we see the total vapor pressure curve, we may even see a point where the vapor pressure of the mixture is greater than either of the pure liquids. As we know that higher the vapor pressure, lower will be the boiling point. So boiling point of this mixture will be less than either of the pure liquids, which is seen in the boiling point composition curve. In this curve, we similarly plot the vapor composition curve. What we see now? We see that there is a point at this particular composition where the vapor composition curve meets the boiling point curve. So at this particular composition, the liquid and vapor will have the same composition while boiling. So the vapor cannot be made more richer in the more volatile component beyond this point by distillation. This mixture is called azeotropic mixture or constant boiling mixture, also called minimum boiling azeotrope. Example of positive deviation is a mixture of ethanol and water. 95.6% ethanol is the azeotropic mixture. Negative deviation. Here, AA and BB bond strength is less than AB bond strength. So, by the same reasoning, the mixture will have lesser vapor pressure than calculated from Raoult's law. It will have negative enthalpy of mixing, that is exothermic mixing. The new AB bonds are stronger and will have lesser bond length, so volume decreases after mixing. In the total vapor pressure curve, there will be an intermediate point which will have lesser vapor pressure than either of the pure liquids. The phase diagram will be like this. At this point, the vapor and liquid composition will be equal. This azeotropic mixture is called maximum boiling azeotrope. Example of this type of mixture is nitric acid and water. 68% nitric acid is the azeotropic mixture.